Episode 10, The Boring Billion. Not all of the Earth's history is dramatic. There were no asteroid impacts, no snowball freezes, no oxygen revolutions. For a vast stretch of time, roughly from 1.8 billion years ago to 800 million years ago, Earth was quiet and the climate was stable. Oxygen levels remained low but steady. The continental drift continued at its usual pace, but no supercontinents assembled or broke apart. Life continued, but evolution seemed too slow. Life continued, but evolution seemed too slow, with little innovation or diversification. The scientists called that period the Boring Billion, and the name fits. If you could visit Earth at any point during this billion-year span, you would find a world that looked much the same as it did 100 million years earlier, or would look 100 million years later. Nothing much seemed to be happening. But boring doesn't mean unimportant. During this billion years of apparent stasis, crucial changes were occurring beneath the surface. In the invisible world of cells and genes and metabolic pathways. These changes, visible to a casual observer, but fundamental to the future of life, were setting the stage for an explosion of complexity that would follow. This is the story of the Boring Billion, of what was happening and what was not, and of why this seemingly uneventful period was actually one of the most important in Earth's history. To understand the Boring Billion, we need to understand what preceded it and what followed it. Before the Boring Billion, in the period of about 2.5 to 2 billion years ago, the Earth was transforming. The Great Oxidation Event has changed the atmosphere and glaciation had frozen and then thawed the planet. Continents were assembling and breaking apart. Life was adapting to these changes, evolving new metabolisms, new defenses, new strategies for survival. After the Boring Billion, from about 800 million years ago onward, Earth was transforming again. A second rise of oxygen levels, the near-Proterozoic oxygenation event, changed the atmosphere once more. Another series of snowball events froze the planet, and most dramatically, complex multicellular life emerged and diversified in an explosion of evolutionary innovation called the Cambrian explosion. Between those two periods of rapid change was the Boring Billion, a billion years of stability, a long pause in Earth's otherwise dynamic history. Why was Earth so stable during this time? What kept the climate from swinging to extremes? Kept evolution from producing new innovations? Kept the planet in a holding pattern for so long? The answer, like most answers in Earth's science, is complex and multifaceted. But several factors seem to have contributed. First, the configuration of the continents may have played a all of the land masses joined together, there is one enormous ocean, the Pacific Ocean, covering the rest of the globe. This creates different patterns of ocean currents, different distributions of heat and nutrients than a world with scattered continents would have. Supercontinents also affect weathering rates, the rate at which rock is broken down and carbon dioxide is removed from the atmosphere. With much of the continent's interior far from the ocean, rainfall may be lower in these regions, reducing weathering and allowing carbon dioxide to accumulate in the atmosphere. The net effect of the supercontinent on climate depends on many factors and can vary over time, but during the boring billion, the presence of Luna may have helped stabilize climate, preventing the wild swings that characterized earlier and later periods. Second, oxygen levels were stable during the boring billion. After the initial rise during the Great Oxidation event, oxygen concentration in the atmosphere settled at the level perhaps 1 to 10% of modern values and remained there for the entire boring billion. This level of oxygen was high enough to support aerobic metabolism of the surface waters, but low enough that the deep ocean remained largely anoxic without oxygen. This created a stable, it's stratified ocean with different environments for aerobic and anaerobic organisms, but without the dramatic shifts in oxygen availability that would occur later. Low oxygen levels also may have limited the potential for complex life to evolve. Modern animals require relatively high oxygen concentrations to support their metabolisms, especially for larger body sizes or active lifestyles. With oxygen at only a few percent of modern levels, the energy available to organisms was limited, and this may have constrained body size and complexity. Third, nutrient availability may have been limited during the boring billion. The ocean during this time appears to have been relatively depleted in nutrients like phosphorus and nitrogen compared to earlier and later periods. This nutrient limitation may have been due to the stability of the ocean without major overturning events, without dramatic climate swings or glaciations to steer things up. Nutrients may have settled into deep sediments and remained there, unavailable to organisms living in the surface waters. With nutrients scarce, biological productivity was low, and with low productivity there was less organic matter being produced, less food for the other organisms, less energy flowing through ecosystems. The whole biosphere may have been running at a lower level of activity than it had before or would after. All these factors, continent configuration, stable oxygen levels, nutrient limitation, combined to create a planet that was stable, perhaps even stagnant. Nothing was pushing the system to make a change. There were no major perturbations, no crises that required an opportunities for innovation, and so for a billion years the Earth coasted. The life continued, of course. Earth and bacteria and archaea still dominated the planet, living in every environment from the sunlit surface to the deep anoxic depths. Photosynthesis continued, producing oxygen, though not enough to raise atmospheric levels significantly. Ecosystems functioned with primary producers, consumers, and decomposers playing their role. But there was little innovation. Few new metabolic pathways evolved. Few new plants appeared. The fossil record from this boring building is sparse, but what fossils exist show organisms that look much like their ancestors hundreds of millions of years earlier. In evolutionary terms, the boring billion was a timeless stasis, a long period when natural selection was maintaining the status quo rather than driving change. But this doesn't mean nothing was happening. In fact, beneath the surface, at the cellular level, one of the most important events in the history of life was occurring. The evolution of eukaryotic cells. Eukaryotes are cells with a nucleus, a membrane-bound compartment that contains the cell's genetic material. This might seem like a small detail, but it's profoundly important. Eukaryotic cells are far more complex than prokaryotic cells, and with internal compartments called organelles that perform specialized functions. The most important of these organelles are mitochondria, the powerhouse of the cell, where aerobic respiration occurs. Mitochondria are descendants of bacteria that were engulfed by another cell in symbiotic relationship billions of years ago. They retain their own DNA, their own membranes, and they reproduce independently within the cell. This endosymbiotic event, the merger of two separate organisms into one, was one of the most significant innovations in the history of life. It gave eukaryotic cells access to enormous energy output of aerobic respirations, far more energy than prokaryotic cells could produce. With this energy, eukaryotic cells could grow larger, they could evolve more complex structures, they could develop specialized functions, and eventually they could become multicellular, with different cells performing different tasks, cooperating to form organisms of unprecedented complexity. But the evolution of eukaryotes was not a sudden event. It was a gradual process that may have taken hundreds of millions of years. The first eukaryotic cells probably appeared sometime during or before the boring billion, though the exact timing is uncertain. The oldest fossils that are definitely eukaryotic date around 1.6 billion years ago. These are fossils of archaeopteryx, simple single-celled organisms with complex ornament that suggest eukaryotic structure. But there is controversial evidence for eukaryotic biomarkers, chemical signatures in rocks dating back as far as 2.7 billion years ago. Whenever they first appeared, eukaryotes remained relatively simple and uncommon. During the occupying similar ecological niches as bacteria and archaea, both but with the advantage of greater energy production and structural complexity. It was not until near the end of the boring billion, around 1 billion years ago, that eukaryotes began to diversify significantly, and it wasn't until after the boring billion in the Neoproterozoic and Cambrian periods that eukaryotes would evolve multicellularity and dominate the visible biosphere. So the boring billion was, in a sense, the adolescence of eukaryotic cells. They existed, but they were evolving. They were developing capabilities that would later allow them to become animals and plants and fungi. But they had not yet realized their full potential. Another important development during the boring billion, though again hidden from the casual observation, was the evolution of sexual reproduction. Sex, in the biological sense, is the mixing of genetic material from two individuals to produce offspring that are genetically different from either parent. Most prokaryotes reproduce asexually, simply dividing into two to create identical copies of themselves. Occasionally, they exchange genes through horizontal gene transfer, but this is not the same as the sexual reproduction. Eukaryotes, in contrast, almost universally reproduce sexually, at least part of the time, and sexual reproduction is crucial for evolving because it creates genetic diversity, mixing and shuffling genes in new combination, producing variation on which natural selection can act. The evolution of sex was probably gradual, emerging first as a mechanism for repairing damaged DNA, and only becoming tied to reproduction. But whenever and however it evolved, sex became a defining feature of eukaryotic life, and it greatly accelerated the pace of the evolution. With sexual reproduction, beneficial mutations could be combined into a single individual, rather than being stuck in separate lineages. This allowed adaptation to proceed more rapidly, allowed organisms to evolve in new capabilities more quickly. So, during the boring billion, while the planet appeared stable and unchanging, the foundation was laid for complexity, explosion that would follow. Eukaryotic cells were evolving. Sexual reproduction. Eukaryotic cells were evolving. Sexual reproduction was developing. Energy production was increasing. The tools were being assembled that would later allow life to escape the microbial world and build the visible, complex biosphere we know today. I think of the boring billion as a long, slow build-up process, a period of preparation. On the surface, nothing much was happening, but underneath, fundamental changes were occurring, changes that were invisible at the time, but would have enormous consequences later. This is the common pattern of Earth's history, and in evolution more generally, long periods of apparent stasis, punctuated stasis is not truly static, but the changes are so slow. The changes are so slow or so subtle that they're not immediately visible. Then when conditions change, when some threshold is crossed, all the accumulated innovations suddenly become relevant, and evolution explodes into rapid diversification. The boring billion was the calm before the storm, the long quiet build before the Cambrian explosion, and while it may not have been as dramatic as the periods that preceded and followed it, it was absolutely essential. Without the boring billion, without the time for eukaryotes to evolve and develop their complex cellular machinery, without the time for sexual reproduction to emerge and create genetic diversity, the Cambrian explosion could never have occurred. Complex life would have. Sorry about that. Complex life couldn't have evolved. So the boring billion, despite its name, was not boring at all. It was a crucial chapter in Earth's history, a billion years of quiet preparation that made everything that followed possible. As we close this episode, let us remember that not all important changes are dramatic or visible. Some of the most significant transformations occur slowly, even over vast stretches of time, in ways that are immediately apparent. The boring billion teaches us patience, teaches us to look beneath the surface, teaches us that sometimes the most important action is happening in the place we cannot easily see. In the next episode, we will see the consequence of all this happening, all this human preparation. We'll witness the eukaryotic revolution, the diversification of complex cells, the evolution of the first multicellular organism. We will see life escape the barely microscopic realm and begin to build bodies, structures, forms that could be seen with naked eye. The boring billion is ending, the stage is set, the players are ready, and the Earth is about to undergo another great transformation, one that will change from a world of microbes into a world of visible, complex, multicellular life. The storm is coming, and it will be anything but boring.